Aloha kako. Hello, everyone. Welcome to Live from NOIRLab at Gemini. My name is Alyssa Leilani Grace, and I will be your host for today's show. Our moderator is Jamika Marshall, and our special guest is Dr. Jinyi Yang. Thank you so much for joining us. Please remember that if you have any questions or comments throughout today's presentation, you can just leave them in the YouTube chat, and Jamika Marshall will read them out loud. Now, Jamika and I are both based in Hilo, Hawaii, as a part of the International Gemini Observatory, a program of NSF's NOIRLab. And Jinyi Yang is joining us from Tucson, Arizona. So before we start our show, I'd like to introduce Dr. Jinyi Yang just a little bit more. Now, Dr. Jinyi Yang got her PhD from Peking University in Beijing, China in 2017, and then joined Steward Observatory at the University of Arizona as a postdoc researcher in the fall of 2017. Her main interests are the studies of distant quasars, the cosmic reionization history, and early supermassive black holes. Would you like to say anything about yourself, Jinyi?
It's a very nice introduction, so yeah.
Thank you. Okay, so let's start with talking a little bit more about the International Gemini Observatory. Now, Gemini Observatory consists of two twin telescopes. One is located near the summit of Mauna Kea on Hawaii Island, and the other is located on Cerro Pachon in Chile. In this way, we have telescopes in both the northern and southern hemispheres, and we can observe the entire night sky around our planet. The international participants with Gemini Observatory are the United States, Canada, Chile, Brazil, Argentina, and Korea. Now, Dr. Jinyi Yang was the principal investigator for this discovery of Poniua-Ena, the second most distant quasar ever found. And this quasar is the most massive quasar found in the early universe at 1.5 billion solar masses. Its name, Poniua-Ena, was given by Ahuahei Noa, which is a naming group based here in Hawaii. You can read more about this discovery on our website at nationalastro.org. Now, Ahuahei Noa, which I just mentioned, is a collaborative effort led by the Iniloa Astronomy Center of Hawaii. And they bring together the discoveries made by the Mauna Kea observatories to Hawaiian students and teachers in order to give these discoveries Hawaiian names. And so it's a really, really great effort. Poniua-Ena in particular was named by a group of 30 Hawaiian immersion school teachers. And for our most recent science update with Gemini Observatory, the Gemini North Telescope recently contributed to the finding of the most distant confirmed short gamma ray bursts. Now, short gamma ray bursts are these cataclysmic events in which a huge amount of energy is released within seconds. This particular SGRB is thought to have formed from the merging of two neutron stars. SGRBs, because of their short rate of occurrence, are very rare to detect, and it was made possible, this observation was made possible by the rapid response rate of the Gemini observatories. And with that, I'll let Dr. Jinyi Yang discuss her research.
So thank you, Elisa. So I will show my slides here. So is everything good? Can you see my slides?
Looks perfect.
Okay, thank you, Elisa. And so I'm Jinyi Yang from University of Arizona. So first, thanks for this opportunity. And today I will introduce my work about searching for the most distant quasars in the universe. So Since I will talk about quasar, so first of all, I will introduce something about quasar, what quasar means, and the discovery of first quasars, some basic properties of quasars. About the discovery of quasars, let's back to 70 years ago. Yeah, in 1950s, radio astronomer in Cambridge at that time, they started to construct a number of catalogs of radio source. They're radio detected source, but they're only radio detect source. And most of these radio source, they were completely unknown before. Yeah, at that time, the angular resolution of the radio telescope was very poor, so it's very hard to measure the accurate position of this object, then find the optical counterpart. So we cannot find the optical counterpart, so we cannot take spectral, we cannot identify this object. And 10 years later, astronomers start to identify this object. They first improve the precision measurement. There's one object I need to mention, that is the 3C273. It's the most famous quasar. That one was identified by using heating of this quasar by the moon. This is a very good method to improve the precision measurement. So after that, astronomers start to find the optical counterpart of this object, and then took spectroscopy. So when we get spectral, so this object, this object could be identified by spectral. And at the same time, there are also several other similar objects has also been identified. And then astronomers start to understand that this is a new kind of object. They're faint, looks like a blue star in the imaging, but they have very strange spectral. The spectral is very different to the star spectral. I will show it later. So, and then astronomers call this object, this kind of object, quasi-stellar radio source. So, since it looks like stars in the imaging, they have radio detection, and some of them do not have radio detection, and then that's the quasi-stellar object. And today we call it quasar. So let's see that there's some examples of the quasar images. So they're all from the 3C catalog. There is 4 objects. The 3C means the third Cambridge radio source catalog. Now we can see there are 4 objects in the center of this imaging, of each imaging. They're all point source, stellar looking. There's no extended structure. It looks like just stars in the image. But they have different spectral, as I mentioned before. So what's the spectral? And it's still this object, the 3C273. So the upper panel, this is a 2D spectral. Actually, this spectral is the first quasar spectral taken by Martin Schmidt in 1963. This is the first spectral astronomer get about a quasar. So we can see in the 2D spectral, there's some emission line. As shown here, we can see the H beta, H gamma, H delta, and also there's a weak oxygen 3 here. So there's some emission line, and compared to the bottom channel, that's the emission line observed at the rest frame. So we can see from the quasar spectral, the emission line looks wavelengths, they're different to the wavelengths at the rest frame. We can see this emission line, this emission lines shift to the longer wavelengths to the right side. So we call it the red shift. And based on the difference of this wavelengths at the observed frame and at the rest frame, we can measure the red shift. So of this quasar, the red shift is measured as the 0.158. So this is the first quasar redshift astronomer obtained. And we can also see this picture. So this picture shows, the right panel of this picture shows the Martin Schmidt appeared on the cover of the Time magazine. So this is an astronomer the first time get a spectral of a quasar and also measure the redshift. So what does redshift mean? What redshift means, now we can see here. As I show in the spectral, the redshift is measured from the difference of the emission lines, the wavelengths of the emission lines at the observed frame at the rest frame. So this redshift is actually the redshift measures of how fast the object is moving away from us. So we can think about the Doppler effect. So if an object is moving away from us, then the spectral lines moving to shift to the longer wavelengths to the right side. So we call it redshift. So why the object is moving away from us? So that's due to the expansion of the universe. So due to the expansion of the universe, object is a more distant object actually is moving faster away from us. So that we will get higher redshift, means the wavelength shifts to redder part. So we call it higher redshift. And also, as I mentioned before, it's distant. So higher redshift is also means more distant than the photons from more distant object. It took longer time to reach us. So the higher redshift also means that is younger. At that time, it's longer time to reach us, means the time the object observed, this object exists at the younger and earlier universe. So about the quasar redshift, when I mention the higher redshift, that means this quasar is more distance and exists in a younger and earlier universe. That's quasar redshift means. And so 70 years passed. Astronomers have already understand a lot of properties of quasars. So here I will brief in summary some basic properties of quasars. And showing here, the first thing I want to mention is quasar is a kind of AGN, is an active galactic nucleus. So it's a galactic nucleus in a galaxy, the central of a galaxy, but it's active. And why it's active, I will mention later. Active is due to the supermassive black hole. So the basic properties of quasar, the first one is compact and stellar looking, as I showed before in the image. And also we can see this is the Hubble Space Telescope image of a quasar. So we can see here, this one, so within the green circle, this one is a quasar. And the other side, we can see that there is a star. So it looks like star. It has a stellar looking. And compared to also, we can see some extended source galaxy here. So, but for quasar, there's no, it's just point source, no extended structures. And quasars are always very luminous. So how luminous it could be? So it's always 100 to 1,000 times brighter than the Milky Way. I see Jamika. Hi, Jamika. Are you coming with questions? Oh, I cannot hear you. Sorry, Jamika. Oh, yeah, it works.
Hello, yes, and again, welcome to everyone in our YouTube audience, and thank you, Dr. Yang, for already seeing that we had a comment that from the audience, actually, more of a question for clarification. You are talking here about emission lines and absorption lines. Could you briefly explain to us what an emission line is and what an absorption line is and why those are important?
And actually, I haven't talked about absorption line actually, but I will show the absorption line later. The emission line, here show the spectral. There's three Balmer lines: H beta, H gamma, H delta. They're from the quasar broadline region. That's the emission line, but I will show the absorption line later. And also, I will show quasar spectral later. Then you will see the emission line and absorption line in the 1D spectral. That will be more clear. Yeah.
Perfect. Thank you.
Yeah. So let's back to the basic property. And yeah, we are talking about luminosity. Yeah, quasars are very luminous. So typically 100 to 1,000 times brighter than the Milky Way. And in addition to these two properties, as I mentioned before, it's an active galactic nucleus. So why it's active? There is a supermassive black hole in the center of each quasar. So what is a supermassive black hole means? First, we can see the image here. This is the famous image of the black hole, the donut image. So this is the black hole of the M87. So, and each quasar, its energy is generated from the metal falling onto the supermassive black hole. The central supermassive black hole is active and is accreting the matter, and the matter falling onto the supermassive black hole. And then that is the origin of the power of a luminous quasar. So how massive these supermassive black holes could be? There are two examples. They're just billion solar mass. So they're 1.2 times 10 to 9 solar mass and 7 times 10 to 9 solar mass. There's 7 billion solar mass black hole of the M87. So there is a center in the center of the galaxy of the quasar. And for luminous quasar, the supermassive black hole in the center of luminous quasar typically are 10 to 8 or 10 to 9 solar mass black hole. That means 100 million to 1 billion, and also some of them maybe 10 to 20 billion solar mass black holes. And this black hole, they're active. They're actively accreting matter onto the supermassive black hole at a rate around about 1 solar mass per year. So this rate is already enough to power the whole very luminous quasar. So it's a very amazing. And in addition to these properties, I will show is the quasar spectra. Then we will see the emission line here. So this figure shows a typical quasar spectra is actually a quasar template. So we can see first to see quasar has a power law continuum. We can see the dashed line, the dotted line. There's a power law continuum, although the power of the slope may be changed at different wavelengths, but they have always the power law continuum, especially at the UV optical. So, and we can also, in addition to the power law of the continuum here, we can also see some flex here, something look like a spike, but it's very broad. We call it broad emission lines. So we can see this is a broad emission line. So the spectra I showed before is a 2D spectral, but this is a 1D spectral. We extracted the signal from the 2D spectral along some lines, and we'll get the 1D spectral. Now here we can see the clear emission line from lemma alpha to H alpha. So in addition to the emission line, we can also see some absorption line features in quasar spectral. But actually, most of these absorption lines are not from quasar itself. So where it's from, we can see here. Here in this figure is again, the solid white line is again the spectra of quasar. So here the right point is the quasar. So when a photon is emitted from quasar and on its way to reach us, it will meet some intergalactic medium, some intervening medium between the quasar and us. Then when the photon meet an intergalactic medium, there will be result in a absorption line here, and it will meet a galaxy. Then we will see a very strong absorption trap here. So we can see it again. So this cool intergalactic medium will result in absorption features showing quasar spectral. And again, we can see when it meets a galaxy, it's a more dense medium related to the galaxy, we will see very strong absorption trap here. So a quasar spectral will tell us all the information about what the photon meets on its way to us. So that's the absorption feature showing quasar. It's a very interesting and also important application of quasar spectral. Oh, I see Alisa. Hi.
Hello. So I have a quick question because I think what you just talked about is so amazing and interesting. So I just want to highlight it a bit more. So when you are studying these very distant young quasars, not only do you get to learn about the quasar itself, but you're also learning about all the material between us and that quasar?
Yeah, along the sight line.
Okay.
Yes. When I just say that just something like the photon emitted from the quasar on its way to us, it will meet a lot of intervening matter. Then the gas will result in some absorption line. So when we meet the photon, when it reaches us, it will tell us information about everything it meets on the way. So it's very interesting thing. Yes.
That's awesome.
Yeah. So based on these basic properties, including both the imaging and some physics about the supermassive black hole, and also we can get some information from the quasar spectral, including the property of quasars and also the intervening mediums. And then based on these basic properties, so if we want to study the early universe with quasars, since it's very luminous, quasars are always very luminous and distant. So with this objects, we can go back to very distant universe, to very, very young universe. How distant we can go to is around, for example, here, we can go to around so far we have used the quasar to go back to around a few hundred million years, just few hundred million years after the Big Bang, just a few % of the current universe age. So with this distant quasar, we can study the early supermassive black hole, and very young universe, and also the early massive galaxy, since as I mentioned, the quasar is actually in a galaxy, it's hosted by galaxy. And also we can, from quasar spectral absorption features, we can learn about the intergalactic medium, the intervening matter absorbers. And also quasar has been suggested to existed in some massive halo. So we can start the formation, the evolution of this massive halo at a very young universe. So that's the way it's actually the basic science goals, why we want to search for these very distant quasars. And also one thing I'm gonna mention is, here, this is spectral. This is the current published redshift record holder, the most distant quasar we know currently actually. As a redshift 7.5. So what redshift 7.5 means? It just means that this quasar is at the universe when the universe is just 790 million years after the Big Bang. So it's very, very young. And this figure shows the spectral we observed, we got from this quasar. So the black solid line here is observed, this is from the signal as the quasar provides us. And the red solid line here is from a quasar template from lower redshift. I mean, just later time, quasar template from a large sample of quasar. So, astronomers usually compare the observed high redshift quasar spectral with the low redshift quasar template. That's one to study the evolution of quasar property, for example, the continuum slope and the broad emission line shape. And so then we can study the evolution of quasar properties. So that is the highest redshift quasar. And actually there's a large number of astronomers, including our group. So we are searching for a large sample of distant quasars, try to understand, to do something statistical to understand more property of the quasar and also the early universe. But what I want to mention is that the quasar, they're very rare in the universe. So the number density of quasars is much lower than the galaxy and also stars. So searching for quasars, it requires the largest survey area, a large sky area. So it's better to have the whole sky coverage to search, to catch one high redshift quasar. And they are also faint. Since they're very distant, so they look very faint. So we need very deep observation, both of the imaging and also the spectroscopy. We need deep observation. And here, at least some typical method used for the quasar selection, quasar survey. The first one, radio, as I mentioned before, this is the method used to discover the first quasars. And the radio survey based on the radio emission of quasar, and infrared survey, and also optical plus infrared colors. I will introduce what the color means. And also the X-ray survey. So this four methods actually they're based on the multi-wavelength properties, multi-wavelength emission of a quasar. And then also we can see some promotion. Promotion means that actually since quasar is a point source, so some stars, dwarfs, these stars are always the main contamination of quasar survey. So we want to separate quasar from stars. But the good thing is stars always have proper motion, so it's moving. So then we can by measuring the proper motion, we can separate the quasar from some moving stars. And also variability. So some of quasar have variability is very variable. So based on this property, we can select some variable quasars. So this is some typical method. And in our program, in our group, we are carrying out a survey. Since 2016, we are searching for quasar redshift higher than 6.5 using the optical plus infrared color method, using this method. So what the redshift about 6.5 mean? That means that the quasars at the universe less than 850 million years after the Big Bang. Oh, I see Alisa again. Hi, Alisa.
Hello. I think you're actually starting to answer the question that I was going to ask, which is, do you use all of these different methods to confirm one quasar, or can you sort of use just a couple? And a follow-up question to that would be, for all of these different methods, do you have to use a different telescope for each one as well?
Yeah, it's a good question. So in our survey for the quasar selection and the quasar identification, we focus on the optical and the infrared in both including both imaging data and also spectroscopy. And there are also some different methods, but actually sometimes we can combine using only one or combine 2 or 3. For example, if we want to combine X-ray variability and radio, it also can improve the selection efficiency, the success rate. And yes, this different method based on different telescopes. For example, radio, we need to use a radio telescope, and the optical infrared we can. In optical infrared, we usually can use the same telescope but different instrument that focus on different wavelengths. And X-ray, we need to X-ray space telescope. So they're from usually from different telescopes. Yes, we need to actually searching for distant quasars. So we need a lot of time of different telescope instruments. It's actually expensive.
Thank you.
And so back to our program about the searching for quasar redshift above 6.5. So as I mentioned, we are using the optical plus infrared colors. So what the colors means. Here in this figure, here the solid line, the white solid line here show is again the quasar spectral. And the dashed colorful line here show the different filters and actually at different wavelengths. We call it at different bands, the imaging at different bands. So this filter can provide us the imaging at different filters can provide us the magnitude of a quasar at different wavelengths. And the difference between 2 bands, the magnitude at 2 bands, we call it color. So we can see, since I mentioned before, quasar parallel continuum, so we can see the magnitude at different bands, they should be different. Then we get the color. So, and also, the quasar spectral is different to the star spectrals. So we get different color of quasars. We will get different colors between quasar and stars. So the colors could be a good way to separate the quasar from contamination from the stars. So, and also to have different redshift, here, this spectral show a quasar redshift 4. So if we want to go into high redshift, we will see the spectral is moving. Here, this line is the strongest feature we typically use to identify quasar. This is the quasar line emission line. So we can see to high redshift, the line line is moving to redder and redder longer wavelengths. And then we will get different color. So this is a good way to select the quasar at different redshift. So based on the colors, as I say that our program is based on the colors, so we should start it with the photometric data, the imaging data first. And the photometric data, they're mainly from these telescopes from the wide field optical and infrared surveys. So for example, the Euclid telescope in Hawaii, and we can also see SDSS, the wide field optical, the famous SDSS, sorry. And also the 4 meter, 2.3 meter that Cape Peak in Arizona, and the other 4 meters in Chile. And we can also see the Pan-Star Y that is also in Hawaii. And again, at last, I want to mention the WISE. This is a space telescope that provides us the near-infrared and mid-infrared imaging data of the whole sky. So it's a very large scale coverage. So based on the photometric data set, we are carrying out a survey of distant quasar in a field around that's 20,000 square degree field, so almost half of the whole sky. Based on the imaging data, the photometric data set, what we can get is there's imaging that looks like this. This is imaging of a very small scale coverage. So we can see there's a lot of objects here. There's some of them are bright, some of them very blue, some are very bright, but some they're very faint. So this is the imaging of our sky area. And so based on this imaging data, we were selected our candidate based on the color method, the color cut method I mentioned before. For example, there's a color cut diagram. So in this color cut diagram, we are using the Y band that's from the Pan-Star 1, and also J band from the Euclid telescope, and also W1 that's from the Y space telescope. So use the color cut diagram, we can see the different quasar at different redshift This is line solid line with the different numbers means quasar at different redshift. For example, from redshift 6 to 6.5, 7, and 7. So this is the quasar color redshift track. That means the quasar different redshift locating at different position in the color space. And also, so we can see some MRT here means the MRT dwarf. They're the main contaminants of our high redshift quasar survey. So this is the black dashed line means that this is one of our selection of our quasar survey. So used to select the quasar redshift above 6.5 to 7. So this is one of our basic selection criteria used to select the quasar candidate. So for example, in the red panel, we can see here this imaging, and we can see the zoomed in part, there is a very red object. That is the one selected by such kind of selection criteria. We can see there's a very red point source. So actually to high redshift, since it's the alpha line moved to very red wavelengths. So it's in the imaging, we expected to see very red point source here. So this one can be a very good candidate. And after we select a sample of such kind of candidate, oh, then I see Alisa. Hi.
Hello. So
Hi.
I have a question about
Sure.
the methodology a little bit here, because it's so interesting. So for this image that you have with all the different galaxies, and you can find the point source of the quasar, do you take images like this on all of the telescopes that you mentioned beforehand, or is it an image on one telescope?
Sorry, Alisa. Sorry, could you please repeat? I cannot. Yeah, I lost that. I cannot hear you.
That's okay.
Sorry.
Can you hear me now?
Yeah. You do the second half.
Okay. So the image that you have here, is that taken, do you take an image like that on each telescope, or is it just one and then you gather data from all the telescopes to create the graph that you have on the left?
Actually, the different telescope, they're focused on different wavelengths. So if we want more color should be more helpful to selected quasars. So if we want to improve the efficiency, the successful rate, we want to collect or imaging from different telescopes. Yeah.
So is this image a combination of multiple pictures from different telescopes?
Yes, actually, yes.
Okay, cool.
But
Thank you.
actually, based on when we selection, we will get not the imaging. Typically, we just get a catalog. We get a lot of numbers. Yeah.
Well, we appreciate the image. It's very beautiful.
Yeah, it's a color stacked one. It's stacked just by stacking the imaging at different bands, different wavelengths. And just stack together, then we can see the color. Yeah, it's good to look, but it's not the real one we use for the selection.
Okay, thank you.
Okay, thank you for the question. And let's back to our candidate. And so when we get the candidate, then as I mentioned before, the discovery of the quasars, they're also based on the spectral. So when we get a sample of candidates, we also want to take spectroscopy and obtain the spectra of each candidate. So for spectroscopy, we still need a lot of telescope time. So so currently we are using these telescopes, the MMT and LBT. There are two telescopes in Arizona, and also the Gemini is the Gemini North. This is the Gemini North, and also the Keck in Hawaii. Gemini actually, it has Gemini Source in the Chile. And we're also using the VRT and Magellan telescopes. They're also in Chile. So based on the observation from these telescopes, we will get a spectral. We will get spectra of each candidate. And what spectral looks like here this is the upper left panel here show the 2D spectral of a candidate of a quasar actually. We can see the bright trees here, the bright white trees here. That is a signal we got from candidate. And along the trees, we extracted this signal along the trees and then get a 1D spectral here. This is the 1D spectral. Okay, it's we are lucky we can see the very strong landmark emission line. As I mentioned before, it's the most obvious feature we use to identify quasar. So we can identify this candidate is a quasar. So for each candidate, we'll do the similar things to identify them based on the spectrum. And using this method, our program, our survey have already identified a large sample of new quasars at redshift above 6.5. So here, this figure shows the example of some quasars spectrals, the 1D spectrals. And also here, we can see in this figure, in the right panel, the figure shows the magnitude actually representing the luminosity. The luminosity and the redshift distribution of these quasars. So go up to this direction means the one object is more luminous, and to this direction it means the higher redshift. Is at a high redshift means at a younger universe. So we can see in this figure there over the red point there is a new quasar discovered by our group. So if you are interested in our survey, you can also search for these papers. There are some main publications of our works. And we can a brief summary about our program of the high redshift quasar survey. So we have already built a new sample of quasars that are redshift 6.3 to redshift 7.6, including 38 quasars. So especially I want to mention that we have some very interesting individuals. For example, the first one, this is the most distant known lensed quasar at redshift 6.5. So what the lensed quasar mean? Here we can see the image. This is a color stack image too. So here the orange part, this is our target, is our quasar. And the quasar, in front of this quasar along the sight line, there is a galaxy in front of the quasar. So this is a foreground galaxy. So when there is a foreground galaxy, the massive galaxy in front of the quasar, and the background quasar will be gravitationally lensed by the foreground galaxy. Then we will see, so as I mentioned before, each quasar is a point source, but since it's lensed, so we will see more than one point source, we will see multiple images. For example, here, for this object, we see 3 images of this object, but they're actually from the same object. So this is the most distant, the highest redshift known lensed quasar. And I see Jamaica, hi.
Yes, thank you, Jinyi. Quick question, could you clarify for us what gravitational lensing is?
Just showing this image, the right panel, this figure. So as I mentioned, there is a background quasar, and there is also a massive galaxy in front of the quasar along the sight line. So between the quasar and us. So the foreground galaxy, we can treat it just a lens. So then the photon from emitted from the quasar, it will be, since the galaxy is very massive, so it will be gravitationally lensed by the foreground galaxy. Then we will see the quasar, then we will see multiple images since due to the gravitational lensing. Typically, it's a complicated way to identify this kind of lensed quasar. Our group we also have a high redshift lensed quasar survey. So when we see the color is a quasar, but it has multiple imaging, no more than one point source. They have the same color and the same spectral, and typically there's a probability that this object could be lensed. It's just that the photons emitting from the quasar, but it's destroyed by the foreground. The light destroyed by the foreground galaxy. So then we will see more than one image of the quasar, the background quasar.
Thank you.
Yeah.
And we actually also have another question from Sabria Mosby. Now, the question is, are quasars dangerous to humans? Now, assuming there was a human civilization near, and whatever near means, but near a quasar, how would that affect humans?
It's an interesting question, but actually, I don't know how to say that. Since the quasar is a very active, just like if a human is near to a supermassive black hole, so how it could be. I think I don't know the exact answer. Yeah, it's very complex thing to consider since the high energy, high luminosity, and also we know, so if anything fall into the black hole, even the photon fall into the black hole, it cannot escape. So that's yeah, that's some answers, I guess. So
it's a complex answer. We appreciate that.
and actually it's almost it's not possible to be very close to the supermassive black hole, since the high energy for quasar always form accretion before the metal fall onto the supermassive black hole. The metal first form accretion disk surrounding the black hole, and out of the accretion disk, umbrella region and narrow region. So it's hard to be too close to the black hole, actually.
Okay, so that answers the question then for Sabria then, because so as these quasars would be forming with that accretion disk, we would not be able to even be close to it. All right.
Yeah. Oh, and actually, since we are in Milky Way, if when the Milky Way is active, I think the active galaxy nuclear also some feedback to the interstellar medium, to the stars. So maybe they were just the first to destroy all the stars. Yeah, first.
Thank you so much. All right, Sabria Mosby, hopefully that answers your question. Thank you.
Okay, so yes, let's back to our discoveries. And after the gravitational lens, the quasar, I also want to mention the 7.5 quasar, the redshift 7.5 quasar. So as I showed before, there's the most distant known quasar, redshift 7.54. So, but there's only this quasar previously known as redshift above 7.5. And from our survey, we discovered the second one. There's a new one, and also this one, it has been given a Hawaii name named as Pernua. So I will introduce this one later. And after that, very recently, we also discovered a new quasar. It's the new redshift record-breaking quasar. So which means that it has much higher redshift than or any other known quasars. So this is a brief summary about our surveys. And next, we will focus on the Pernua. So as I mentioned, this is a new redshift above 7.5 quasar. So it's the second most distant known quasar, and just 700 million years after the Big Bang. So we can see still very, very young universe at that time. And although it's the second most distant quasar, but this is the most distant quasar hosting a billion solar mass black hole. So which means that this one has a more massive black hole than the other quasar at similar redshift. So, and this is our paper, and so this is our team. I see Elisa.
Hello.
Hi, Elisa.
I have a question that I hope will be kind of fun about Pernua. And that is, so with your discovery of it so early in the universe, 700 million years after the Big Bang, we are living in a point now 13 billion years after the Big Bang, right? So I'm just wondering if you have any insight as to what Pernua could look like right now. If we could follow it along its life, what does it look like at this time?
Yeah, actually, it's a very good question. This is what astronomers want to learn, how the quasar evolve with the cosmic time. And there's some ideas about the quasar evolve, and actually in the local universe, the quasar is at that time is active, and there's some duty cycle. It couldn't be active all the time. So after some time, they may just it's not active again, and after some time it maybe died. Yeah, we may see some elliptic, very wide, massive elliptical galaxies that could be the counterpart at the local universe of the high redshift supermassive black holes. That could be, yeah.
Okay, cool. Thank you.
And I see Jamaica again.
Yes. Yes, thank you. Okay, so in the previous slide, you were talking about the mass of this quasar, that is the most distant quasar hosting a billion solar mass black hole. Could you briefly explain how we measure the mass of a black hole, or of anything that we can't actually touch?
Wow, cool. This is a very good question. How we can measure the supermassive black hole high redshift quasar. And I can show it in the next slides. I will show spectral. Actually, we measure the black hole mass of high redshift quasar based on the emission line in the spectral. Yeah, I will show it next. Yeah.
Okay, perfect. Thank you.
Yeah. And so, as I am showing our team here, is our team to discover this quasar. Yes, we should thanks to the program which gave us a Hawaii name of this quasar. It's Paniwana, which means unseen spinning source of creation and surrounding with brilliance. Thanks for this beautiful Hawaii name. This is also the first quasar to receive an Hawaii name. And also, as I mentioned before, so our program is selecting quasar first started with the photometric data. So it's also the same to this quasar. It's also selected first based on the photometric data. And this one is from this survey, the imaging surveys from the decals, PS1, Pan-STAR1, UHS, and WISE, as we can find these surveys in this map. So it's covering a very large wide field. And so based on the first imaging, the data selection, the color selection, we applied the color diagram method to this imaging data and get around a few hundred such kind of candidates. So this quasar is just one of the few hundred candidates. Yeah. So when we get this is some example of the image of this quasar. So we can see this image of this quasar different wavelengths at different bands. So the Z and Y means PS1Z and PS1Y with the Z and Y band from Pan-STAR. And here the other Z and Y means the Z and Y from the decals. So, and also the JHK. Oh, sorry, the Z band is from decals and the YJHK is from the U-curve imaging. And so since it's a very, very high redshift quasar 7.5, the landmark emission line has already moved to the wavelength longer than 1 micron. So this quasar can only be detected at the near infrared. So we can see it detected in the YJHK band, but not detected in the optical Z and Y band. So this is the image of this quasar. And after the image, we just took the spectroscopy of a sample of candidates. And this quasar was first observed with Gemini North telescope in last May. So this picture shows the Gemini North and the dome is open. We can see telescope inside. And the red one, the red panel of the figure show this is a 2D spectral we get from the Gemini genius of this object. So we can see here, this is the trace. Now we can see there's a break. Here this means that there is a very strong landmark emission line. That's how we identify this quasar with this 2D spectral. And by extracting 2D, we get 1D. Then I can answer the question how we measure the black hole mass. So this is a 1D spectral of the rest frame of the quasar in the rest frame UV optical. So we can see the rest frame wavelength here. And we can see the black line here is the black solid line here is the observed quasar spectral. So we can see continuum first, and also some broad emission line. And one of the emission line here, this one we call it the maximum 2 emission line. And this maximum 2 emission, based on fitting the emission line, we can get the shape. We can get the line wise. So based on the line wise, we can measure the black hole mass. Since there is a relation between the line wise, we're assuming that this is line wise. This line is broadened by it's just virial broadening. This is a virial component. So we can. The line wise represent velocity, and there are also a large number of astronomers. They're working on the broadline region size, and so when we get the broadline region size and also the line wise from the broadline the magnitude 2 line, then we will measure the black hole mass, the central black hole mass. So this is the typical way used for very high redshift quasar black hole mass measurement. And in addition to the UV optical spectrum, so this quasar it has also been observed with Keck, Magellan, ALMA, Euclid, and GCMT for multi-wavelength property studies. So we will notice that there, the Keck, Euclid, and GCMT, they're also on the Mauna Kea. So thanks to Mauna Kea, we can observe this quasar. So based on the ALMA observation, so that's at the 7 millimeter, we get a fan stretch line, named a C+ line. So this line can provide us a very accurate redshift measurement of a quasar. So based on this measurement, this spectrum, we get the quasar redshift is a 7.515. And this is what we get from the spectrum. And next, I will mention what we can learn from this new discovery, not only the spectrum, not only the black hole mass measurement. So something we can try to constrain the black hole growth, the early supermassive black hole growth. So there's a question actually with the more and more observations of this high redshift quasars. Astronomer has already raised a question that how this observed in this figure, we can see here in this corner, the observed supermassive black hole as from the high redshift quasars. How this supermassive black hole grow from which kind of seed black hole? So there's three different seed black hole model, but they're just the models from theoretical model. There's model predicted seed black holes. There are different kinds. For example, the direct collapse and from a giant unstable gas from a direct collapse from a giant star from the unstable gas, and also dense star cluster, and then stellar remnant of the POP3 stars. So this different seed black hole, they can occur. They can occur at different time, probably just 100 million years to 200 million years after the Big Bang. So we can see that between the seed black hole and our observed quasars, there are just few hundred million years. So how this supermassive black hole grow up to such massive black hole in just few hundred million years? It's very short time. So that is the key question we want to answer with this high redshift quasar observations. So and also you can see this is the press release of our Pernilla. So in the press release, we can see left panel show the seed black hole that just 100 million years after the Big Bang, we can see they're just very dense, probably just we can see very dense skies here, but it's not the real thing. It's just the impression of the seed black hole. And after that, what we observed at the 7 million years after the Big Bang, at that time, there's a very powerful black hole here with a very massive host galaxy. That's our observed quasar. It's also ionized surrounding neutral gas here. This is so how they grow up from a seed to the supermassive black hole. That's we want to study based on these high redshift observations. So let's see the science data here. In this figure, this is the result from our from the measurement of Pernilla. So we can see the right point and also the right solid line. The right point here, it means the measurement of the supermassive black hole. We can see here is 1.5 billion solar mass, and also compared to some different color. This colorful point here, that's from some previously known high redshift quasars, a similar redshift or lower redshift. So this solid red line means the black hole mass, the black hole growth track is a track of the supermassive black hole from early time. For example, from the redshift 30, we assume that this black hole started to grow up at redshift around 30. Then we will get this track. Looks like this. And we will, based on our measurements and the growth model, we can get the constraint on the seed black hole mass. Let's see here, this is seed black hole mass. It requires the seed black hole around redshift 30. That's with 10,000 solar mass. It's very massive seed black hole. Now we can see compared to the other results, the different line here. or for other quasars, they just requires less massive seed black hole. So we can see this quasar, the interesting of this quasar is this supermassive black hole, it requires the most massive seed black hole than any other known quasar. As I mentioned before, in this model, we assume that this seed black hole started to grow up at redshift around 30, but actually redshift 30 means 100 million years after the Big Bang. It's a little bit earlier. So based on some main model, it should be later. The growth of seed black hole or the growth of the existence of seed black hole should be later than 100 million years ago, million years. Then we just to later time we can see if we assume that it started about 15, then we need around 300,000 solar mass. This is very massive. It's a challenge into the seed black hole model. So based on this measurement, based on this result, so our quasar, this supermassive black hole is more consistent with the direct collapse black hole seed model. As I mentioned before, there are 3 different models. So this result, this constraint on the seed black hole mass, then prefer the direct collapse black hole seed model. But I should say that we cannot rule out any other model, but it prefer the direct collapse. So this is what we can learn from this supermassive black hole. And actually, we are to understand more about the quasar and high redshift quasar, high redshift supermassive black hole. We are also searching to try to build a larger sample of quasars above redshift 7. So this is an ongoing program. And at the end, I want to show something about the redshift record, the evolution of redshift record of quasar over the time. So we can see this is the discovery of the first quasar almost 60 years ago. And that based on the radio technology. And to high redshift, we will use optical, and now we will also include the infrared colors. So we can see almost 10 years, with almost 10 years, we can improve the redshift record with step around redshift 1. So that's very interesting things. So we are here now. So when we can reach redshift 8 to 9, based on the prediction, that's just a simple prediction. It couldn't be real. Maybe we try to find the high redshift quasar faster earlier, but based on the prediction here, we can reach the redshift around 8 to 9 in 5 years later in 2025. Yeah, that's just an interesting prediction. Okay, I see Alisa. Hi.
Hey, Jinyi. I was just going to let you wrap up your final slides if you'd like. We have about 2 minutes left of our presentation today. So if there's any more questions or comments from the YouTube audience, please post them and Jamika will read them aloud. Thank you so much for being here with us. I do have one question actually to ask you while we wait for other questions and comments. So your goal is to find more of these quasars further than redshift 7, right? Do you think that the next age of large-scale telescopes will help you to accomplish that?
It's a very good question. This is just for my the last slide. Yeah, yes, we need the next generation telescopes for high redshift, for more distant quasar survey to go deep, go more early universe, go to more younger universe, and go distant. Yes, they're including some space telescope. We can see Euclid, JWST. We know JWST will launch in next October next year, and also WFIRST, and some very large ground-based telescopes, for example, RST, GMT, TMT, ELT. Actually, TMT, ELT, the diameter of this telescope more than 30 meters, so it's very huge. Yeah.
All right, thank you so much, Dr. Yang. We have one final comment here from our YouTube audience, and this is from Sabria Mosby, and she says, this was a great learning experience about quasars. So I would like to thank all of our YouTube audience for tuning in today, and for those of you who posted your comments and questions for Dr. Jinyi Yang. Thank you very much.
Thank you.
Do you have any last things that you'd like to say, Dr. Yang?
Actually, this is the last slide. I just want to say, we are trying our best to find the highest, to find the higher redshift quasar. The final goal is one try to find the first quasar to understand the question that when is the first quasar.
Okay, thank you so much. Thank you for being here with us today. Thank you to Jamika for moderating and for everyone for tuning in. We'll see you next week with another Live from NOIRLab.
Thank
Bye.
you.